Welcome back, everybody. What we're going to do today is talk about Chapter 8. We're going to start with Section 1. So right now we're essentially dealing with Section 8.1. And we're going to talk about drawing inferences from samples to populations. So we've been dealing with some background work, looking at normal distributions and z-scores, so that we can understand some basics that are needed for computing basic inferential stats. And we're at the point where we can almost put it all together. And we'll be able to do that by the end of this particular chapter. But first, in section 8.1, we're going to have a brief discussion of sampling distributions, which is mostly a review from chapter 5, so that we can put together everything that we've learned so far. Let's jump right in. In Chapter 5, we discussed central limit theorem and how it can be used to produce a distribution of sample means. Let's review that real quickly. First, you might recall that according to the law of large numbers, the mean of all rolls when we were looking at dice should approach the mean that we would find in the population, the true mean. So for example, it's easy enough to see what the true mean should be when we're looking at one die and rolling it many, many times, because every option on those 6 sides of a die, is equally likely to come up. So a 1, a 2, a 3, a 4, a 5, or a 6. Those options are all equally likely to come up when you roll one die. Well, over the long run then, we should find that the mean of all those rolls should approach 3.5. All right, well, we referred to this distribution of rolls of that individual die as the parent population of individual scores. They're based on these individual rolls from one die. But then we were able to take our discussion up a notch and create what we call the distribution of sample means. And this was created by taking 1,000 rolls of 2 dice. And each time we rolled those 2 die and we had 2 outcomes, we would take a mean of those 2 values. And every time we computed a mean for each of those 1,000 rolls, we would plot the mean value. That right there is a distribution of sample means. Well, according to central limit theorem, we wouldn't have to actually go through all that hard work in this case and roll 2 dice 1,000 times. We already know how this distribution is going to look. According to central limit theorem, the shape of this distribution of sample means will be relatively normal. And as the sample size increases, here we had a sample size of 2 dice at a time, the mean of this distribution of sample means will approach the mean from the parent population. And also the standard deviation of this distribution of sample means, what we call the standard error of the mean, will decrease. So let me just demonstrate these last couple points with a couple graphics here. This now is a distribution of sample means based on taking 5 dice and rolling them at one time. So our n is increasing. And we can see here that the mean of this distribution of sample means is coming closer now to that true mean from the population of 3.5. And we can also see that this standard deviation, also known as the standard error of the mean, is getting lower. So our sample size increased, our mean of this distribution became closer to the true mean, and the standard deviation decreased. And when we say that the standard deviation decreased, what we're showing is when we roll those 5 dice and we can compute a mean, that mean that we compute is starting to come closer and closer to that true mean every time. So there's less variability from one sample mean to the next. Now let's go ahead and take not 5 dice at a time, but 10 dice at a time. And we can see again that we have a relatively normal distribution. Again, because we increased our sample size, the mean of this distribution of sample means is now very, very close to the mean of its parent population. Remember, this mean really over the long run will be 3.5. And we can see again the standard deviation decreased, showing that the mean from those sample means, all those sample means, are coming closer to that true population mean. In other words, there's less variability from one sample to the next because our sample size has increased. All right, well, that was just kind of a basic point that we learned about central limit theorem and how it related to sampling distributions. So this kind of sums up the important points about a distribution of sample means. Populations we know are typically large, so we can't usually compute all those sample means from scratch by ourselves. to create a sampling distribution. And we don't need to, because according to central limit theorem, that distribution of sample means will have the following characteristics. One, we saw that its shape will be normal. And the nice thing about that is if we have a normal distribution, we can use that z-table that we've been using to compute basic probabilities and percentiles. We also know about its characteristics. So this distribution of sample means will have a mean. We often refer to its mean as the expected mean. That's why we see a mu sub e. The mean of that distribution of sample means will be equal to the mean from its parent population. So that's really easy for us to understand and for us to know. We just simply know that when we create the distribution of sample means, its mean will be equal to the mean of that parent population of individual scores. We also know another important characteristic. We know about the variability in that distribution of sample means. Remember, standard deviation is a measurement of variability. Well, in this case, the standard deviation of that distribution of sample means is also known as the standard error of the mean, and that is represented with this symbol. You might recall that the sigma represents a population standard deviation, and when we put the little x bar in here, now it's representing the standard error of the mean. It's just a standard deviation of that distribution of sample means. And we can use this formula right here to compute it. So the standard error of the mean will be computed based on taking the standard deviation from the parent population and dividing by the square root of the sample size. There are some interesting things that come from that, and we just want to make sure that we understand it conceptually. So this is showing variability from one sample mean to the next, and so that's kind of showing us too that each sample mean is different. No one sample mean perfectly represents the population. There's variability from one sample to the next. And because there's variability from one sample to the next, we have sampling error. Sampling error is simply going to be the average distance between our sample mean and the true population mean. So when we're talking about sampling error, we're essentially talking about how close is our sample data coming to the population data. So remember, this is what's really tying us to inferential statistics. Our sample data is not going to perfectly represent our population data. And if it's not going to perfectly represent the population data, we need some way to quantify how far off it is. Well, that's what sampling error is all about. So if we use sample data to learn something about population data, sampling error is going to be involved in that equation. Well, we needed to talk about all of this stuff, these distributions of sample means and sampling error, so that we can quantify how much of a difference there is between our sample data and that true population data. So the bottom line is that sampling error is measured by this standard error of the mean. Let's go through a quick example where we can put some of those concepts into use mathematically. 8th grade standardized test scores form a normal distribution with a mean of 400, standard deviation of 70. I think we went through an example like this previously. We're just trying to reactivate those memories. What's the probability that an entire school of 8th graders, so imagine there are 100 people in that school, we have a sample size here of 100, will have a mean score below 375. So I'm trying to figure out what's the probability of finding data this extreme or more extreme from a distribution that has a mean of 400 and a standard deviation of 70. So we see that value is obviously below the mean. What's the probability of finding a sample of 100 people that would have a mean that low? All right, well, we can use our z-score formula to figure that out. All we need to do now is take 375 and transform it into a z-score. Remember, a z-score is just a standard score, and once we transform any score, like this one right here, into a z-score, we can then find the probability of finding it essentially just by chance. So what's the probability of finding a value this low or lower? So in order to use our z formula, which is shown right here, it's just shown up here essentially in words, we're going to need to know our sample mean value, which we have, that's 375, the population mean value, which is 400. So we're seeing differences that we actually observe between our sample data and the average population value. And we want to divide by the standard error, which is looking at differences we would expect between the sample data and the population data just by chance. So differences we observe over differences we expect by chance. So we already have the values for the numerator. Let's compute the standard error of the mean first. So we need the population standard deviation, that equals 70. And then we want to divide by the square root of our sample size. Our sample size is 100. So we need the square root of 100. Let's simplify that. 70 divided by 10, that would be, so that's pretty easy to do in our heads. We would find that the standard error equals 7. All right, well now that we know standard error for down here, we can plug everything else in. So we take our sample mean of 375. We're going to subtract our population mean, which is 400. So here we have the differences that we're actually observing relative to differences between means that we expect by chance, which we just computed is a value of 7. 7 points, essentially, on this standardized test. So we found a difference of 25 points, and we divide that by 7. Okay, let's pull out our calculator and work that out real quickly. So we have 25, and that's actually a negative value. And we're going to divide that by 7. See what that equals. Negative 3.57. Okay? Negative 3.57. All right, let's go ahead and look that up in our z-table. So let me open up the z-table that I have already. And remember, a z-score of -3 is already starting to be very large. We know that within one standard deviation of the mean is 68% of all scores. It works the same way with standard errors. Within one standard error is 68% of all sample means. Within 2 standard errors is 95% of all sample means. Within 3 standard errors is 99.7% of all sample means. We're more than 3.5 standard deviations below. So we're going to take the closest value. We're looking for -3.57. This is our closest value. And we see it's in the 0.02 percentile. So that's even much less than 1%, 0.02%. All right, so how would we summarize what we found here? So according to table 5.1, the z-value corresponds to the 0.02 percentile. So there is a 0.02%, that's 0.02%, chance that a random sample of 100 students will score below 375. In other words, it's really rare that we would find a value like that just by chance. All right, we're getting close to being able to put all this together. We're just kind of refreshing our memories of how to do this stuff. Let's go through another example. Texas has 225 farms where acreage forms, the amount of acreage for these farms forms a normal distribution where the mean acreage equals 582 acres and the standard deviation equals 150. So not all the farms are of this size. There's some variability, but this is the average farm size. For random samples of n equals 100, what is the mean and standard deviation for the distribution of sample means? All right, we can compute that pretty easily, just simply based on information here from the parent population. So what if we're going to take random samples of 100 farms, all combinations? What's going to be the mean and the standard deviation of that resulting distribution of sample means? Well, according to central limit theorem, we can create that distribution. Well, once we do, we can figure out what's the probability of selecting a sample of farms with 100 farms in that sample that has a mean greater than 600. Well, based on what we know about central limit theorem, we already know that the expected mean is going to be equal to the mean of the parent population, which in this case equals 582. 582 acres. We also know about the standard error of the mean. So as we're trying to understand the distribution of sample means, here we can figure out its characteristics just according to central limit theorem. So we know about the standard error of the mean because we can compute it based on the characteristics from the parent population. We know that the standard deviation equals 150 in that parent population. And we can divide by the square root of the sample size. In this case, the sample size is equal to 100 to find the standard deviation in our distribution of sample means, otherwise known as the standard error of the mean. So we can simplify and solve that. We take 150 divided by the square root of 100, which would equal 10. And 150 divided by 10 is going to equal 15. So we're talking about 15 acres. So in that distribution of sample means, we know that the mean is going to be equal to 582, and the standard deviation of that distribution of sample means will be equal to 15. So that's representing differences between the sample means that we would expect just by chance. So how far off are the sample means from the true population mean? Well, they tend to be off on average by about 15 acres. So now we can answer a question like this. What's the probability of selecting a sample of farms with a size of 100 that has a mean greater than 600 acres? Here we can use our Z formula. So we take the sample mean, in this case we're dealing with 600 acres. We subtract that true population mean of 582, and then we divide by the standard error of the mean, which equals 15. So we're talking about differences that we're actually observing between that sample mean and that true population mean over differences that we expect just by chance between sample means. 600 minus 582 equals 18, and we want to divide that by 15. Let's figure that out real quickly using our calculator. 18 divided by 15 equals 1.2. 1.2. Okay. Well, we can look up that value in our Z distribution. So I want to look up 1.2 right here. I see that that's in the 88th percentile. It's in the 88th percentile. So heading back here, as we interpret our results, we can see that according to the table, the Z value corresponds to the 88th percentile. So we're trying to figure out here what's the probability of finding a sample of 100 farms with a mean acreage greater than 600. Greater than 600. Well, we found that 600 acres is in the 88th percentile. So what proportion is beyond that? What proportion is greater than 600? That would be 12%. So there's a 12% chance that a random sample of 100 farms will have a mean greater than 600 acres. All right, so in this case, we wanted to figure out what proportion was greater than 600 acres. Our table shows us the percentile. You'll recall that the percentile is showing us that 88% of the sample means are at that value or below. So if I wanted to figure out what proportion were at that value or above, I would need to figure out what's above 88%. There's 12% left. All right, so again, this would be relatively rare that we would find 100 randomly selected farms that have average acreage of 600. We'd find that about 12% of the time. All right, well, we can take this same discussion and apply it to proportions. So just a quick review here. The distribution of proportions below represents 32 responses to the question, do you plan to vote in the upcoming presidential election? So we asked 32 people, and we're just recording yeses and nos. And we can easily compute a sample proportion, and you might recall that a P with a little hat on it represents a sample proportion. So in order to figure this out, we would simply look at the number of people who say, yes, I plan to vote. And if we count up all the yeses, we'd see that there are 24 of them. And we divide that by the number of people who we asked overall. So we've got the number of yeses over the number of all outcomes. And in that case, in this particular case, it equals 0.75. So we're talking about proportion being 0.75, or 75% of the responses are yes. So when we have non-quantitative data like we do here, yeses and nos, there's nothing quantitative about it. Previously, we were looking at issues like numbers of acres. That was clearly quantitative. That's where we're using means. Now we need to use proportions when we have non-quantitative data. So we can look at a distribution of sample proportions just like we can a distribution of sample means. So this should look pretty familiar. We can go through this relatively quickly. When we're looking at a distribution of sample proportions, it's going to have the same characteristics as the distribution of sample means. Its shape will be approximately normal. We know that mean of the distribution of sample proportions will be equal to the mean of the proportion for that population. So we call that the expected proportion. So that will be equal to the proportion for that parent population, the population proportion for the parent population. And then, of course, there's going to be some variability in that distribution of sample proportions. And that, again, is simply measured by the standard deviation. So instead of looking at a standard error of the mean, now we're looking at a standard error of the proportion. And it is denoted with this symbol right here. Again, the sigma always represents the symbol that we use for standard deviation. It's a measurement of variability. And when we see the little sub-sample proportion, we know that we're talking about a standard error measurement. So we can use this formula to compute it, and all it's really looking at is, on average, how much are the sample proportions differing from the true population proportion. So it's a measurement of variability. Well, when working with those sample proportions, sampling error is simply going to be that average distance that I just described, and it is simply measured by standard error of the proportion. All right, so everything is essentially identical to how we were looking at the distribution of sample means, but we're not looking at means anymore. We're looking at proportions because we don't have quantitative data. So let's run through a quick example with that. The population of proportions of actual voters equals 0.6. So let's say we know that, over the long run, looking back, about 60% of people vote in a presidential election. So we ask 32 registered voters if they plan to vote, and 75% say yes. So, we see a difference there. The question that we're going to ask is, what's the probability that we'd find a difference like that just by chance? And the way we typically ask that question is, what's the probability of finding a difference like this or a difference more extreme just by chance? So that's what we're asking right here. What's the probability of selecting a sample of voters? So what's the probability of finding 32 random voters who have a proportion saying that they plan to vote greater than 75%? Well, we're going to use essentially the same method as we used with the means, but we're just going to modify our formulas to deal with the proportions. Our standard error is now based on proportions, and our z-score is now based on proportions. But in general, it's got the same setup. We look at our sample proportion, we subtract the population proportion, and divide by the standard error. So we're looking at differences that we're actually observing. So differences that we're actually observing right here between these values over differences we expect by chance. So let's first compute those differences that we would expect by chance. Differences between sample proportions that we would expect just by chance, measured by the standard error of our proportion. So in this particular case, we want to take the true population proportion, which is 0.6. We want to multiply that times 1 minus 0.6. So that's going to equal 0.4. We want to divide by n. Our n in this case equals 32. And then we don't want to forget we need to take the square root of all that. All right, so this is going to take just a couple steps. Let's just simplify and solve that. We can take 0.6 and multiply by 0.4. And just to make sure we don't make any mistakes, let's use our calculator. So 0.6 multiplied by 0.4 equals 0.24. So this equals 0.24 in our numerator divided by 32. And again, we don't want to forget to take the square root eventually. So let's do the division real quickly. We'll take 0.24, which is already in my calculator, and then divide by 32. That equals 0.0075. Let's just round that to 0.01. In general, in our class, we just go to 2 decimal places just to keep things a little bit simpler. So we have 0.01, and we need to take the square root of that. So again, we just kind of walk through it step by step so everybody's on the same page. So let's just take that 0.01 and take the square root. There's my square root key. Square root of 0.01 equals 0.1. 0.1. All right, so now we know the value for our standard error. So we take our sample proportion, that equals 0.75. We're going to subtract the population proportion, that equals 0.6. So these are the differences that we're actually observing, divided by the differences we expect just by chance, 0.1. 0.75 minus 0.60 equals 0.15 divided by 0.1. That's going to equal, let's work it out with our calculator. Sometimes it's just confusing to deal with numbers that have decimal points. 0.15 divided by 0.1. That equals 1.5. 1.5. So our z-value equals 1.5. So we want to figure out what's the probability of selecting a sample of voters with a proportion greater than 0.75. Well, now we know where 0.75 is in the distribution. It's 1.5 standard errors above the mean. So let's find that in our z-table. And in order to answer this question, we're going to have to see what's beyond that percentile. So we're going to look it up in our z-table. We're looking up a value of 1.5, and we can see that's quite high in the distribution. It's at the 93rd percentile. Well, we want to see what's beyond that. So if that's at the 93rd percentile, so this z-value corresponds to the 93rd percentile. So we now need to figure out what's the chance that a random sample of voters will have a proportion greater than that. That just leaves 7%. So there's a 7% chance that a random sample of 32 registered voters will have a sample proportion greater than 0.75. All right, well, these particular calculations are going to be necessary for us to work on the next couple sections where we estimate population parameters. So we've just learned the last little detail that we need to put everything together. And we will put everything together and start answering some interesting questions about population data in the next couple sections. So that was the key content from section 8.1. For now, that is all.